Hello, I am an aerospace engineering student at the University of Alabama, and recently, just over my winter break, I decided to practice some with Ansys Fluent. And after trying to brainstorm a project idea, I decided to check if Shrek's ears take on their iconic cylindrical shape as an evolutionary advantage to reduce drag. My hypothesis was that because cylinders have a much lower drag coefficient than the cup shape of regular human ears, the shape of Shrek's ears evolved as a way to reduce energy wastage due to drag force. So I began by doing some very rough hand calculations to get an idea of the numbers I should be looking for when I eventually throw this into CAD. Um, like I said, both of these calculations are extremely rough, and the shapes have been heavily simplified. Um, so both shapes have been simplified to 2D shapes that extend infinitely into the page. And to begin, I took measurements of one of my ears with calipers and then scaled the measurements up by a 1 to 3.76 ratio in order to match Shrek's head, which is much, much larger than mine. So first I did human ears, and I plugged these numbers into the equation for the drag force. For the density, I assumed a temperature of 70 degrees Fahrenheit, and I assumed a speed of 6.25 meters per second, which, after doing some research, seems to be about the average human's jogging speed. And I'll include all of my sources for this stuff in the description below. So plugging all of these in gave me a value of 2.86 newtons, and that is for one ear. I then repeated this same process for Shrek's ears, which I instead simplified to a circle, extending once again infinitely, and doing this gave me a value of 0.332 newtons per ear. And so obviously this is much lower than the drag force for the human ears, which is mostly due to the decreased area, and also the coefficient of drag is nearly half of what it is for the human ears. So before we go into my process for creating the models in CAD, here's the measurements I took in Blender using a model of Shrek I found on Thingiverse, and I changed Shrek's height in the model, obviously, to match his quote-unquote real height that I found online, which was 7 feet. So my next step was I used Solidworks to make some CAD, which I could use as a basis for my CFD simulation. So I started with making the Shrek head. So obviously the head itself is not very detailed, like what real Shrek's head would be. For my purposes, that's not very important because I'm more interested in the ears and comparing them. Also, I cut the head in half, and I'm only doing one ear just to cut down on computation time. I made this pretty quickly. It was just, I used a revolve for the head, scaled it to make it kind of more the head shape where it's longer rather than wide. Then for the ears themselves, I just used a loft. This cut was for cutting the head in half. And then I shelled out the ear to make it like a real ear where it would have a hole through it. And then I used an intersect to make it all one body. After that, I moved on to the human ears, which were a little more difficult, but still just used a loft. And it was mostly the same process. It's the same head design and everything. So after that, I moved on to actually setting up my CFD. So I will be using Ansys Fluent for the purposes of my CFD. And so my first step was to go into Space Claim and to clean up the model. And the things I always check are stitch, gaps, missing faces, split edges, extra edges, duplicates, small faces, simplify, and inexact edges. And basically, I just go through, click them, and if there are issues, I solve them. And I just go through a couple times until I'm coming up mostly clean. So then after that, I import the models into Design Modeler. The process in Design Modeler is very quick and easy, actually. I just import the model as a frozen, use an extrude to create a domain around it, create my name selections, inlet, outlet, symmetrical, and then I use a boolean to cut the head out of the fluid domain and create a name selection based on the faces of the head. The meshing was also relatively simple. Really, all I had to do was I deleted the contacts from the connections folder. This is because I've found in the past that it causes a lot of issues and it's not necessary for the purposes of this simulation. Then for the mesh, all I did was add an inflation layer with a maximum of 8 layers. And here's my mesh. As you can see here, we have our rectangular inflation layers before moving out to the regular mesh. So for the simulation, I once again assumed a speed of 6.25 meters per second. The simulation with Shrek Ears converged after 204 iterations and gave me a drag coefficient of 6.7 and a drag force of 4.1 newtons. And that is for half the face and one ear. So for those of you who are curious, here is the plot of my scaled residuals. Looking here at the contour of static pressure, we can see that the highest pressure occurs at the leading edge of the ear, which is to be expected as this is where the stagnation point in the flow is located. Finally, here are the path lines generated by the simulation. For those of you who like the pretty animation, I think the most interesting part of these path lines is here inside the ear. You can see the little vortex forming from the air spinning around in there, and then you can also see the flow staying attached down the bottom of the ear before detaching here and continuing with free stream. So I'm not going to go over the setup for the human ear simulation because it is essentially the same as the setup for the Shrek Ears. So once again, here are my scaled residuals. Looking at the contour of static pressure, we can see, as expected, a high pressure zone forms in front of the ear and a low pressure zone behind. The pressure is well distributed throughout the surface of the inside of the ear due to its large cross-sectional area. So next, let's look at the path lines created by this simulation. So for the human ears, I think that the most interesting part of the path lines simulation is right here. As you can see, there's a little vortex that goes from the bottom of the ear to the top. So I just find that to be pretty interesting. As you can see, because the ear's got a larger area, it is having a pretty large effect on the air entering the free stream. Alright, so now for the moment of truth. Do Shrek's ears reduce the force due to drag and thus give him an evolutionary advantage? Unfortunately, it appears that they do not, as with the human ears, the drag force was reduced to 2.5 newtons, which is 1.6 newtons lower than that given by the Shrek Ears. The drag coefficient also was reduced from 6.7 with the Shrek Ears to 4.1 with the human ears. This means that Shrek's ears are an evolutionary disadvantage in terms of the energy wasted due to drag. However, I'm absolutely sure Dreamworks didn't just make this design decision based on looks. So if anybody has other ideas for why the ogres evolved in this way, please leave it in the comments. In addition, if you have any advice for me on my simulations or methods, please leave them in the comments. As I said earlier, I am a university student, so I always welcome advice from those more experienced than me, because only through practice and critique can I improve. All of the sources I used in researching this project are in the description below, and thank you for watching and have a great day.